Well, I'm tired of laying down long. You don't care to listen, you don't care at all, and you don't understand as to what it means to be with a man like me, yeah. Treat me kind with love all the time and tell me for what you need, yeah. The first time I trouble, you're gone to the devil, and I don't mean to burst your bubble, but I love you, and now I'm gonna miss you, and bye-bye. And I'm tired of breaking down the wall. You just keep your distance, and you don't care to call, and you don't understand as to what it means to be with a man like me, yeah. Treat me kind with love all the time and tell me for what you need, yeah. First time I trouble, you're gone in the double, and I don't mean to burst your bubble, but I love you, and now I'm gonna miss you, and bye-bye. Come on, boy! And I'm tired of waiting for the fall, and you make no commitments, you can't have it all, and you don't understand as to what it means to be with a man like me, yeah. Treat me kind with love all the time and tell me what you need, yeah. First time I trouble, you're gone on the double, and I don't mean to burst your bubble, but I love you, and now I'm gonna miss you, and bye-bye. Take it home, boys! Come on! And I'm tired.
Okay, so today we're going to look at heaps that we started last time. Remember I showed you this picture. This is a min heap. From the visualization, you can see the two properties that we're going to discuss here. The first property is the fullness property. The fullness property is that every child is present at every single level except possibly the last level. And in that case, they're full to the left. So in this case, you've got every single node that is present at every level. So 1, 2, 4, and 8. And then these last two are all the way to the left. Right? So it would be wrong to put a node right here because that would leave a gap right here. Right? It would be wrong to end up deleting one of these nodes here because that would be a gap higher up in the tree. So what we need to do is we need to make sure that that fullness property is satisfied with whatever we're going to do with it. It also satisfies the heap property. The heap property is that the key of every node is less than both of its children, if they exist, of course. That's going to be a min heap. Why do we call that a min heap? Where's the minimum element in this heap? It's all the way at the top, right? Of course, you can reverse that and flip it, and you can have what's called a max heap. It doesn't really matter because when you go to implement something like this, you implement it using a comparator. And all you need to do is implement a min heap. And if you want a max heap, what do you do with your comparator? You flip it, you reverse it, right? And it becomes a max heap. And now the maximum element is at the top. So we're only going to look at min heaps. Let's make some observations here. The first observation is, as we started out with this discussion, that the depth of the heap is going to be logarithmic. Why is that? Because again, how can we exploit this structure? We went through the analysis as if we have a full or nearly full binary tree, then it has guaranteed depth of log n, right? So there we're going to get a guarantee on the depth that we did not get when we looked at binary search trees. The other observation is that the minimum element is always at the root. How can we exploit these two things, right? If we can make the operations for this data structure to be order D, then they're automatically going to be efficient. However, it is not a general purpose data structure. Right? We're not going to be able to do, say, an arbitrary search. For example, how would you find, I don't know, 70 in this tree? Right? If I started here at 1, would I know that it's down here in the left subtree or the right subtree? Not necessarily. Say 65, right? Instead, I would end up going and exploring this entire left subtree, half of the elements before I get to the right branch over here, and then find 65 over here. If I wanted to do a BFS, a pre-order traversal, in-order traversal, doesn't matter. I'm going to end up looking at least at half of the elements. It's going to be efficient to find the minimum because it's always going to be at the top. What about the maximum? Could I find the maximum? Where's the maximum here? Is it on the last level? Is 92 the maximum? Nope, it's over here. I would have to check everything at the last level and the second to last level to find the maximum. Of course, I could ignore the parent of anything in the last level, but that's besides the point. Half of the elements are going to be down here. The other half are going to be up here. Right? Even though I've only cut out half of them, I still have n divided by 2 of them, which is still going to be order n. Right? This is not a general purpose data structure. Instead, this is a restricted access data structure. Restricted access data structure. We've heard of this before, right? Yeah, I spelled that right. Structure. No, I didn't. All right, start over. Data structure. There we go. It's a restricted access data structure. I think it's correct, even though it's highlighting it as wrong. Data structure. Yeah, it is, right? But probably because it's 2 words. Fine. Data structure. There we go. So this is a restricted access data structure. What other data structures have we looked at that are restricted access? You can't just do whatever you want. Here's my stack of dishes. Can I just rip this dish out from the bottom or the middle? Nope. I'm only allowing you to work at the top. And if I restrict your access to pushing and popping off the top, then everything is efficient. It's all order 1. Right? A queue. If I restrict your access to to offer and to pull, everything P-O-L-L, pull, then everything is efficient. A deck is a generalization of those two where you can do both operations at both ends, and again, it's going to be efficient, but only because I'm restricting your access. So how am I going to restrict your access in this case? I'm only going to support 2 operations. Get and remove min, right? And insert or add element. There we go. Very, I don't know, Python-y there. Get and remove min element, right? And then add an element. This is called a heap for a reason. If I were to throw something on the top of this heap, right? Think of this as a big giant heap of garbage. Do you have any control over where it ends up? Right? No, sometimes it'll roll down halfway. Sometimes it rolls down all the way over here. A heap of stuff is somewhat unorganized. And just throwing something on top of the heap of a clothes or garbage or like a sand pile or something, a heap of sand, right? You have no control where that one grain ends up. It could end up way down at the bottom. It could end up at the top, right? So we're not going to have any control over where we add stuff. We're just going to throw it into the heap. Get and remove min. That seems like really convenient, right? Why? What's the minimum here? Get and remove it. All right, well, this is a preview of an application of this. 1, right? Great. That means that 1 is gone from this heap. Eventually, we're going to fix this heap. What's going to end up at the top? Remember, it's the heap property. The minimum has to be there. Since 1 is gone, it's no longer the minimum. What ends up being at the top? 5. If I get and remove that, I've got 5 there. There. Now they're both gone. What ends up being at the top now? 30. Do you start seeing a pattern here? 40 is going to be next. 50, 55, 80. Actually, no, not 80. What am I saying? What's next? It wasn't 55 either. It was, what's going to be next after that? Oh, I missed 45 down there too. 45, then 50, then 53. You get the idea. Right? If I pull stuff out of this heap, what's going to end up being the structure that I pull out? A sorted list. Right? So this has its uses. Right? What I could do is I could throw everything into the heap. Right? Where it ends up, I don't care. Because if I start getting and removing everything, then when it comes out, it's magically sorted. Again, that goes back to the theme of this course. Smart data structures and dumb code are a lot better than the other way around. Throw everything in there, pull everything out of it, and it's magically sorted. The data structure was responsible for all that stuff. Right? Both of these are going to be order D, which of course, as we've already observed, is going to be order log n. Right? And this is also going to be order D, which is order log n. Why is that not working? There we go. Now you're math mode. Okay. All right. How do we go about doing them? Right? So let's look at get and remove. Get and remove. No, let's look at add element first. Add element. Right? So let's go ahead and come over here and start with this heap. And suppose that I want to add another element here. I don't know. Add 44, let's say. We're going to ignore duplicates again, right? That's just a technical issue, right? All right. So add 44 here. Well, can I just throw it up on the top of the heap here, and then it ends up wherever it's going to go, right? I don't know. Well, if I started 44 here, right? If it was sort of a binary search tree, it should go right? Because 44 is greater than that. Oh, it should go right because it's greater than that. 44 is less than 80, so it should go over here. It's less than 90, so should I go ahead and hang it off over here as the new left child of 90? What is that? A gap. We cannot have that. Right? Not only that, but is it the heap property satisfied? I was trying to treat it like a binary search tree, and it ain't a binary search tree. It's a heap. Right? So the first thing what I'm going to do is I'm going to preserve the fullness property. Okay? How do I preserve the fullness property? Where could I put this element right here so that it is still full, and the last level here is full to the left? What's the next available slot? Left child of 53. And I'll go ahead and put 44 in there. Okay. Right? So the fullness property is still satisfied. But is the heap property satisfied? Look at 53. Is it less than both of its children? It only has one child, so is it less than 44? Nope. We can fix that, though. How would you fix it? Just swap them. All right? Okay. And what are we left with? 53, there we go. So 53, nope. 53, and then this ends up being, what did I just insert? 44. Right. Now, I look at the parent. Is the heap property satisfied now? Nope, still not. So once again, swap them. And this is now 44, and this is now 55, or 50, excuse me. All right, there we go. All right, now is the heap property satisfied? 44 and 5 over here? Yes. Right. And what about this? Should I have considered any children over here that I might have screwed up? Right. What was here before? 50. And so I'm going to move 44 up here. Well, if you replace this with something that's even less, then that just means that it's going to satisfy the property even more. All right. So no, I don't have to worry about anybody over here. If I instead had inserted, instead of 44, if I instead inserted 0, what would have happened to 0? It would have ended up all the way at the top. In any case, what I do is I insert it as the last element. Right? So step 1 is going to be insert the new node as the last element. Right? And I don't know how to do last yet, but we'll understand this once we look at an implementation of it. Then I heapify. Right? You compare it with its parent and swap if out of order. until either A, the heap property is satisfied. Like I did here, I stopped short. I stopped right here. I did not have to go any further. Or the other part would be that it becomes the new root. Or B, it becomes the new root. Right? Because there's nowhere, you don't want to fall off the edge of the tree on the top of the tree now either. Right? That's called heapify or fixed heap, sometimes it's called. In any case, this is going to be order D comparisons, assuming that we can jump to the last element easily, right? Or at least efficiently, right? Now, if I gave you this tree just as this diagram, right? And remember, you only have access to, say, the root. Are you going to be able to jump to that location immediately? No. In fact, what if this entire thing was full all the way over here, right? You had 2 children there, 2 children there, 2 children there. Would you even know, starting here, that the next element is in this part of the tree or in this part of the tree, right? Here's the next element that I need to add. There's not enough information there unless you can figure out the mathematics of it, right? And for that, I would encourage you to read the book, because 1 year I just went through the mathematics and figured out how it works. And yes, you can find the last element or the next available element by going left or right, just looking at the size of the heap, right? All you need to do is look at those series, right? Summation of powers of 2, and say, okay, no, the gap is over here. Do the math again and say that the gap is over there. Do the math again and say that the gap is over there. And you can travel left and right. In other words, it'll still be order D if you need to do the math. Otherwise, we're going to look at an even easier way, right? Later, okay? But otherwise, it's going to be order D comparisons, and because D is going to be log n, we've got our guarantee on the add element here. Right? We do at most order D comparisons. What about remove and return the min element? Okay? How are we going to do that here? Well, the first thing I'm going to do is I'm going to save it off into a temporary variable over here, because I have immediate access to the root node here. And then I'm going to delete it. Right? It's gone. I've saved it off because I eventually want to return it. But I've left a gap, right? And if you're trimming the tree, right, and if you cut down here at the bottom, right? I mean, if you want to kill the tree and chop the tree down, or the tree is already dead and you need to chop it down, you go ahead and chop it at the root, right? I don't want to do that here. I want to trim from leaves, okay? Now, we did the same thing with binary search trees. I said, all right, well, we've got a gap here. We can go to the left tree and we can go all the way over here and find the maximum value and put it up here. That's for binary search trees. We can't do the same thing here. If I did that, then I would end up finding, I don't know, if I went all the way over here, I'd put 70 up here. That means that I would end up deleting this, and then we've got our gap. Right? We can't do that. So, suggestions. What could I take in this tree and put it up at the top to preserve the fullness property? Not necessarily the heap property, but at least the fullness property. That guy right there. Let's put him up there temporarily. 63. Right? And that means that I've essentially deleted this node right here. Gone. There we go. Is it full? Yes. Does it satisfy the heap property? No. So all I need to do is pull out that same trick that I used before. Right? 63 is not less than both of its children. Could I take 30 and put it up here and swap those two? Would 30 be less than 5? Nope. So I do have to be careful here. I don't just swap the child and the parent. I have to be cognizant of which child I swap. I swap it with the min. Right? So I swap these two. And I am left with, let's go ahead and delete that. 5 comes up here. Come on. 5 and 63 came down here. Right? Is the heap property satisfied now? Nope. I swap it with its with its minimum child, whether or not that's the left or right doesn't matter, and this becomes 50, and this becomes 63. Is the heap property satisfied now? Nope. So I do one more swap here with the minimum, and this becomes 53, and this becomes 63. Is the heap property satisfied now? Yep. I had to heapify that all the way down to the bottom of the tree, right, or as a leaf. Right? Again, it's going to be order D. So do be careful on that. You have to choose which child to do. Right? So to remove and return the min element, save the root off into a temporary variable. Right? Then replace the root with the last element. Right? Then heapify. Heapify downward. Or downward. Swap this element with the minimum min child until the heap property is satisfied, or you reach the bottom of the tree. Satisfied. There we go. Again, at the end of the day, it's going to be order D, because you're always operating in the depth of the tree or the heap, right? Okay. How do we go about implementing this? I could, of course, create tree nodes like I've done before. Tree nodes are going to have a left child, a right child, and a parent. Right? But there's an even easier way. It's really cool. What I'm going to do is I'm going to give you a BFS ordering of this. 1, 5, 30, 50, 55, 40, 80, 60, 53, ... Right? All of it. And I'm going to put it in something that looks familiar. An array. Right? Now I am going to put an extra element over here that I'm going to ignore. That's going to get an index 1, a 0, excuse me. Index 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. Right? Now, if I'm at a particular node, say 55, can I get to the parent? Can I get to the left child? Can I get to the right child purely through indices? Right? So 55 here, that's going to be, let me highlight it. 55 is right there, and there's 55 right there. Okay? It's at index 5. Index is equal to 5. Let's see if we can find a pattern. What about its left child? It's 72, and I didn't keep going. I should have kept going. Let's do it. All right. Continue it off down to the bottom. 53, 72, 70, and those are going to be indices 10 and 11. Right. So continued, continued, ... There we go. All right. So its left child is at index 10. Its right child is at index 11. Where's its parent? The parent is 5. 5 is at index 2. Right. Let's look at another example. What about 5 itself? Right, so let's go ahead and highlight this in a different color. Blue. 5. There's 5 right there. Right. Here is another example. At index index 2, right? That's the value 5 right there. This up here with this is the value 55. Where's its left child? Where's its right child? What indices? So 5, 50, and 55. 50 and 55. So 4 and 5. 4 and 5. What about the parent? The parent is 1. That's going to be at index 1. So mathematically, what do you... did I make a mistake?
No.
Oh, okay, go ahead. Yeah.
Well, like the parents at half of it, like floored down.
Okay. If I'm at index I, where's my parent?
I divided by 2, rounded down.
I divided by 2, floor. I like that. Right? Why floor? What if it was at index 5 and you divided that by 2? Is there an index 2.5? No. So you went floor on that. What about the left?
Is it double it, I think? Yeah.
Yep. It's going to be at 2i. What about the right?
2i plus
2i plus 1, right next to it. Right? Really cool trick. Right? Here is a visualization of it. And there we go. Right? So if you are at index I, you, then your parent is at I divided by 2, and your left child is at 2i, and your right child is at 2i plus 1. Now, it can still work if you use 0 indexing. It's just that everything is off by 1 and it looks ugly, right? And so what we're going to do is we're going to burn that first index, and our indexing is going to start at 1, right? That just means that you ignore this first element and that you're wasting a few bytes here and there, right? And that you're always going to make sure, you need to make sure that you've got room enough for everything. Right? Why didn't we do this to begin with? Right? Why didn't we do this with a balanced, with like a binary search tree? Let's come over here and let me show you something else. I mean, this seems so cool. Why don't we use it? Right? In fact, this is many years ago. Somebody came back from a Google interview and they asked me, I got this question at Google and I wasn't sure. Why don't we always use arrays to represent binary search trees? Or binary trees, always, right? Because the same structure is in a binary search tree, right? All right, let's go ahead and create a new binary search tree. And we're going to add, not 76, but we'll go into a for loop for int I equals 10. I is less than or equal to 100, I plus plus. There we go. And what I'll do is I'll say tree.add, add or insert, what was it? Add I. Right. And what I need here is a comparator, tree utils dot comparator. There we go. And let's go, did I show you the Tixie tricks last time? Okay, good. Because let's go ahead and visualize this. What is this going to look like if I insert all those elements in that order? Oh, come on. No. Oh, is this a runaway? Oh, no, it's just really, really deep. I only wanted power, I only wanted 10s here. 10, 20, 30, 40, 50. Otherwise, it was just way too deep. And it aired out. LaTeX just aired out on me, trying to go with a tree that was 100 levels deep. Don't try to print that out. There we go. All right. Tell me what an array of that tree would look like. It's of depth 9. Right? There's only 10 elements in there, but it's of depth 9. How many elements? How big of an array would I need? I would need an array of size 2 to the 9 plus 1 minus 1 in order to hold everything. That's going to be 2 to the 10th minus 1. In other words, how big is that? 2 to the 10th is going to be 1024 minus 1. So it'd be 1023, size 1023 just to hold 10 elements. 100 times as big. Now, think about that depth 100 tree that I just screwed up. Plus. Now there are, well, we'll start at 1 here. Right? Now there are 100 elements in that tree, but it's a linked list and it all goes to the right. Now how many elements are in there? Or how big of an array do you need? 2 to the 100 plus 1 minus 1. Right? I don't even know what that is. You're approaching what, half the atoms in the known universe, right? Does your computer have that much memory? No, mine doesn't either. And that's why we don't use arrays always to represent binary trees. But we do with respect to heaps. Why? Because they have this fullness property, right? There's not going to be a gap in here, right? With this one, there would be huge gaps. There would be exponentially sized gaps between an element and its left child and its left child and its left child. those would all be, or sorry, right child, right child, right child. Right? There would be huge exponential gaps right here. Another twice as big gap right here, twice as big gap right here, twice as big gap right here, all the way up to 2 to the 100. And that's why we don't. Right? We don't have that many atoms, much less memory, right? Okay, in the universe. So we use this instead. Okay. All right. I don't know. Do we want to look at? We've got 20 minutes here. We can do something with it. Right. New class. I'll call it a heap. Right. Some elements here. I don't know. Do we want to do this, or do we want to see the payoff? Payoff? If we want to see the payoff, then I can do something else on Friday instead. Maybe JPA or something like that. So, what's the payoff here? I can put stuff in, I can take stuff out. And when I take it out, there's the minimum element. I could use that to sort things. Input, a collection of elements. Right? A. Call it A1 through AN. Right? My output is going to be here, A sorted. Okay. Basic sorting algorithm. Right? But unlike, say, quicksort, unlike merge sort or tim sort, this is not a clever sorting algorithm. All I'm going to do is create a heap, H, min heap. And then for each element, A in A, H dot add or insert A. That's it. And then, while the heap is not empty, I will say output H dot get min. That's it. I put stuff in, I take stuff out. 2 while loops. In fact, this could be this is a for loop that you could say that this is a for loop for I equals 1 up to n, because I'm putting n elements in there, right? So I don't need to say that it's not empty or something like that. Right? But I put stuff in, I take stuff out. And that's it. It's sorted. Right? Now, this is a dumb algorithm. I mean, it's dumb code, right? Put stuff in, take stuff out. This right here is a clever, smart data structure. Dumb code and a smart data structure are a lot better than the other way around. Think about quicksort, right? And how you had to program that in lab 13 or whatever. Lots of clever stuff that you probably just copy pasted or something from either the book or some other source, right? This, why would anybody even bother copy pasting this? All it is a for loop and a for loop, and you call a function and call it a function. And it ends up being sorted, right? The payoff, however, comes whether or not it's efficient. Because quicksort was a good sorting algorithm because it was order n log n. Merge sort was a good sorting algorithm because it was efficient. Is this efficient? I have no idea. Let's find out. So, iteration 1, 2, 3, 4, dot, dot, dot. You have to consider how much it costs you to put stuff in on each iteration, right? Remember that we've already said that adding an element is going to be order D, and order D is order log n. But not everything, if I've got 100 elements, not every 100 element starts out in the heap. The heap starts out empty. Right? So the size of the heap is going to start out at 0. After I've put in that first element, its size becomes 1. After I put in that second element, its size becomes 2, 3, dot, dot, dot. When's the last iteration? The last iteration is n, and it has a size n minus 1. Okay? So the complexity of insert is going to be order log the size of heap, which is going to be this right here. All right? So let me clean that up. The complexity here is going to be, well, you can't, but is log of 0 defined? No, you don't make any comparisons. You see that the tree is empty and you create a new root. So you don't end up doing any comparisons and we can ignore that. But log of 1. You make 0 comparison, well, you do make technically 1 comparison, so this would be like +1 or something here, right? Don't worry about those details. Right? Log of 2, log of 3, right? In other words, the size of the heap is growing, and so it's costing us more and more and more to insert stuff until you get down here and it's going to be log n minus 1. Right? You have to add all of this up to determine what the total complexity of the add iterations are. Okay? So log of 1 plus log of 2 plus log of 3. And I think we did this before. Somebody asked what happens when you do something like this. And I appealed to your log identities. This is equal to the summation of I equals 1 up to n minus 1, not of I, but of log of I. Right? If I just took 2 of these things, log of A plus log of B, what's that equal to? Log AB. Right? So do that for all of them. Right? And this ends up being log of 1 times 2 times 3 times ... times n minus 1. Now, give me another label for the thing inside the log. N minus 1 factorial. Now with big O analysis, we're only interested in an upper bound. So to make this a little bit cleaner, I'm going to say that this is log of n factorial. We all agree that that's bigger, right? Okay. All right, well, what's even bigger? If I replaced each one of these with an n, that's what I did here, right? I replaced this n minus 1 with n. What if I also replaced 1 with n? N. Right? Remember, n cannot be negative because n is capturing an input size. Right? So I'm making it bigger, 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 bigger. This is going to be n n's is what? N raised to the power n. Give me one more log identity. How can I take this exponent and move it out front? N log n. Cool. So this phase right here is going to be order n log n. No fancy code at all. Smart data structure. Throw stuff in. Take stuff out. This is the exact same analysis, but instead of going 0 to n minus 1, we go n minus 1 down to 0. Right? In other words, it's also going to be order n log n. We've got a free, efficient sorting algorithm that uses an array, right? And only costs us order n log n. Right? This is called heap sort. It's efficient, it's easily representable, and man, it's awesome, right? So why is it not the de facto sorting algorithm? Well, in practice, you know, TimSort beats it out, or they think TimSort beats it out. It does require a copy of an array because you need to heapify it, and then you need to pull stuff out. There are ways of doing it, I think, in line, but then it ruins the complexity, or it makes it a little bit more bad to use in practice. And again, this goes back to the theme of this course, right? Smart data structures. Dumb code, right? That's going to be way better, right? I don't know. There we go. There. I don't have a sad one, right? Smart code. And no data structure. Or dumb data structures, like say an array, right? This would be quicksort. Recursion, right? And smart, like clever code, right? Do I have something bad? Bicycle is bad? I don't know. Do I have anything else? I guess here, rainy cloud, right?
Just make the raindrops.
Rainy and then a sad cloud. There we go. So smart data structures and dumb code are way better than the other way around. And that's how you can, again, tell the difference between somebody that's gone through a coding boot camp for a year or something like that, and somebody who has a much deeper appreciation for when to use a data structure, when not to use a data structure, right? Looking at something and saying, nope, that loop is terrible because if you use a linked list, that's going to take you 20 years for a billion elements, versus 3 seconds if you had used an array list instead, right? Iterating over that multiple times, a for loop within a for loop within a for loop, that's a huge red flag right there, right? Rethink what you're doing, right? What data structure can we use to pull off the shelf and just use this? This is also called, a min heap is also called a priority queue, right? So do you remember queues? Here, let's just go over here. Right. A queue is a data structure that does not allow line jumpers, right? So we've got something here with a priority, 5, 7, 8, 3, 2, 5, 9, right? And let me put something else at the beginning here, 1, right? So what I want is a priority queue, now serving the next person with the highest priority. That person comes out of the queue and they're replaced with the person with the next highest priority. Not 5, but instead 2 here gets to jump to the head of the line. They have the highest priority. That looks like a heap to me, because if you grab the minimum element, then the next minimum element immediately jumps up to the head of the line or the top of the heap, right? That's called a priority queue. What happens when somebody comes in with, say, priority 10, right? Well, who cares? We'll put them wherever we want. They'll be served in their time, right? What happens when we have somebody with a even higher priority, say 0? Well, we put them here at the end of the line, but then they make their way forward until they're at the beginning of the line. Right? A heap is an efficient and easy implementation for a priority queue. Right? All right, so there's the payoff. Right? Heaps, priority queues have a lot of applications, right? And really, really simple implementation. I think that they're over here in Java, priority queue, foo. There we go. Yeah, well, let's bring it in, import that, Java util. There we go. It's an abstract queue. How does it represent stuff? Where is it? So here, default initial capacity 11. Oh, there it is. How does it end up doing it? With an array, using this indexing trick that we just covered. This right there, right? It uses that indexing trick right there. In fact, you can find the code for it for wherever that indexing trick is. And there's the initial capacity. Find 2 times, or something times 2. There's nothing like that. They probably actually shift it. There it is. There. The child is k times 2 plus 1, right? Hey, that doesn't look like multiplication to me. What is that doing? Have you seen that left? No? What you're doing is, so this is another extra thing that we'll end on here. So if you eventually you'll take some systems level course. And what you can do here is take a binary number, say 7. That's 111. I could shift it by 1 bit, right? And when I do that, I get 1110. What value is that in base 10? 14. Hey. Shifting it by 1 bit multiplies it by 2. Now what if I shifted it the other direction? What if I shifted it that way? then that means I would have 11.1, but it's an integer, so what happens is truncation, and we have 1. What value is that? 3. In other words, this thing divided by 2, 4. Right? So, nice little trick here that you can multiplying by 2. In fact, if you ever write multiply by 2, it's going to replace it with some bit shift, right, like this. And this is 1. If you wanted to multiply by 4, right, x times 4, or x times 4, right, multiply by 4, then what I could do is say x shifted over by 2 bits instead of 1 bit. Shifted over by 3 bits, and that's a multiplication by 8. Powers of 2. It's way easier to shift a bunch of bits in a register than it is to do the actual math. Right? Divided by 2, multiplication by 2. You've done this since grade school, by the way. Right? If you wanted to shift over by 1 decimal, what were you doing? Multiplying by 10, right? Recognize it because you have 10 fingers and 10 toes. But a computer doesn't. A computer has zeros and ones. And so everything that it does is in base 10, right? That's why we call it floating point numbers, because the decimal there, it can float this way, it can float that way. Doesn't matter if it's base 10, base 2, whatever, right? Floating point numbers. Then a whole bunch of other, complex stuff here. I would never have written it this complex, but they're way smarter than me. Like this is, I don't know what this is doing. Like less than half. Say what? This? Where do you mean? Where's the this?
The triple.
Oh, the triple one? That's a cyclic bit shift. So 1 1 1 0 1 1. If I cyclically shift this over, say 2, what that means is I'm going to shift it over. So normally it would shift over 1 1 1 0. But what happens to these 2 at the end? They fall off the end. Oops, come on. They fall off the end and end up over there. Right? So it's a cyclic shift. If this one falls off because I'm shifting it that way, then it just goes back around to this side. Right? Whether or not it's useful. It's useful if you are not treating them like numbers and you're treating them like flags. And then you can do bit masking, and it's called bit twiddling, right? You twiddle your thumbs, right? You're just screwing around with the bits in order to get powerful stuff. Happens all the time with that's why the ASCII text table is set up the way that it is. If you want to go from a capital A to a lowercase a, you flip one of the bits, and that's it, right? And so all those things are really, really efficient. Or you mask it with something. Or you look at one of the bits and you know immediately that it's a decimal, right? Or you do something else, right? That's all bit masking and bit shifting and bit twiddling all together, right? That's what the 1 ampersand, that's a bitwise and. The 1 vertical stroke, that's a bitwise or. And then you can start masking things together and using every single bit of an entire 32-bit integer. That's like a 230, 231 topic. So, all right, we'll end it there, and then we'll talk about JPA on Friday instead. That means I actually have to do it.